KCET 2025 aspirants, so I welcome you all to our KCET Master Stroke series, and in today's video we are going to do one shot from the chapter Structure of Atom. So this is a very fundamental chapter. You don't have to study more, just revise the formulas of Bohr's postulates. Okay, so I'll be discussing that. So Bohr's postulate and quantum numbers are the most important topics in this chapter. So what all things we'll be covering in today's class? So quickly we will see the atomic models, nomenclature, then not nomenclature, this is atomic models, developments leading to Bohr's model, then Bohr's model and quantum mechanical model. Okay, so this is not from this chapter. Okay, next, weightage wise, you can see every year consistently one question has been asked, and this question is either from your Bohr's theory or from your quantum numbers. Okay, so first we will see today atomic models. So we have these all atomic models, right? Thomson model, Rutherford model, atomic mass and mass number. We will see isobars and isotopes and limitations of Rutherford model. As this is not very important topic, so I am not going to be in very much in detail, just I will be telling you the different models what were there. So first of all, Thomson model was called as a plum pudding model. In this model, what happens, it was considered that atom is a completely positive sphere, and on that we have small electrons embedded on it. The negative charge electrons are embedded on it. This was also called as watermelon model or plum pudding model because of the symmetry. Okay, so if you are if you are having one watermelon, you can imagine the whole red part is the positive sphere and the seeds on it as your electrons negatively charged. Okay, so that was your Thomson model. Next, coming to Rutherford model, so he did an experiment where he took a gold foil and he bombarded alpha particles to this gold foil, and he kept a detector behind the gold foil. Now it was observed that in this alpha particles there were three basic major observations. It was observed that most of the alpha particles passed straight through the gold foil without any deflection. The second observation here was, you can see here I have written, so most of the alpha particles passed through the gold foil with, just a minute, yes, most of the alpha particles pass through the gold foil undeflected. And what conclusion we draw from this? That most of the space in the atom is empty. The second observation was small fraction of the alpha particles was deflected by a small angle. Okay, small number or small fraction of alpha particles was deflected by a small angle, and this shows that nucleus, one positively charged nucleus, is present at the center. And the third one, very few alpha particles was reflected nearly by 180 degree, means direct reflected back, and that shows that nucleus is very small as compared to the atom. Okay, so these are the observations and the conclusions. So finally Rutherford gave the model of the atom where he said that in the atom at the center there is a positively small charged dense sphere which is called as your nucleus, and electrons are revolving around the nucleus in circular paths called as orbits. Okay, electrons and the nucleus are held together by electrostatic force of attraction. So this was the model given by Rutherford. Now let us see what is atomic number and mass number. So for example, you have an example of carbon 6 and 13, suppose I write carbon 13, right? So 6 is the atomic number. Okay, atomic number, what does it tell? It is equal to number of electrons, and 13 here is the mass number. Okay, mass number is equal to number of number of protons plus number of neutrons. Okay, protons plus neutrons. This one written. One more thing that I want to say here is this atomic number is represented by Z and mass number is represented by A. Okay. Next we have what is isobars and isotopes. So isobars are those elements where the mass number is same, atomic numbers are different. You can see mass numbers are same, atomic numbers are different. Isotopes are those elements where you have atomic numbers same and mass number different. So I have given a wrong example. This is like this. Okay, so you have atomic number same and mass number different. These are called as your isotopes. Next we have what are the limitations of Rutherford model. So the first limitation, it could not explain the stability of the atom, and it says nothing about the distribution of electrons around the nucleus, means how the electrons are present around the nucleus, it doesn't tell anything about that. Okay, so next we will go, so if we have some questions here, what is the isobar of this one, right? So isobar means what? The mass number should be same, so I can say option number C. Next, find out the number of neutrons, protons and electrons in the given molecule, in the given atom. So this is what? First you have to find neutrons. So neutrons is 37 minus 7, that is 20. So I have only two options. Then I have protons. Protons will be 17 and then electrons will be same as protons. So option number C. Next, which of the following statements is correct regarding the cathode rays? Okay, so cathode rays originate from the cathode. Yes, the charge and the mass of the particles constituting the cathode rays depend on the nature of the gas. So next, the charge and mass of the particles constituting the cathode rays do not depend on the cathode material. They possess kinetic energy. Not correct. So it is given that here it depends, okay, depends upon the nature of the gas. No, cathode does not depend on the nature of the gas. Okay, next question number 7 here. According to Thomson's model of an atom, the mass of an atom is assumed to be uniformly distributed over the atom. Okay, uniformly distributed. So that is why option number A. Rutherford experiment on scattering of alpha particles showed for the first time that the atom has nucleus. Okay, Rutherford told that there is a positively charged dense sphere at the center, that is nucleus. Now we will go to the next part, that is how the Bohr's model came to existence. Okay, so before the what all developments were happening that gave us the Bohr's model. So on that we have the wave nature, the particle nature and the quantization of the energy levels. So next, what was the Bohr's model? We'll see the postulates and the limitations. So before the Bohr gave his model, there were three developments that took place. That was your wave nature, particle nature and quantized energy levels. Okay. So if you see, as I told you, there are the developments that took place before the Bohr gave his model. One is your dual nature of electromagnetic radiation, another was your atomic spectra. Under dual nature of electromagnetic radiation, that says that electromagnetic radiations both have wave nature and particle nature. And the particle wave nature, we already knew that electromagnetic waves are they have wave nature, but particle nature was established by two important experiments, that is your black body and photoelectric effect. Let me repeat once again what I am saying. So developments that led to the Bohr's model where your dual nature of electromagnetic radiation and another was a hydrogen spectra. Dual nature of magnetic radiation says that electromagnetic radiations have both wave nature and particle nature. We already knew that electromagnetic waves have wave nature, but what led us to know that they also have particle nature? That was your black body radiation and photoelectric effect. After that, atomic spectra, lines of spectral hydrogen, emission and absorption spectra we have to understand. So first of all, coming to the wave nature. So wave nature, electromagnetic waves are having both electrical and magnetic fields, and here we have this formula E is equal to C by lambda. Okay, so sorry, not C, hc by lambda. So certain formulas that you should be knowing here. E, or the energy of an electromagnetic wave, is h nu, where h is Planck's constant, nu is the velocity of the wave, or this V can be written as C by lambda. So we get E is equal to hc by lambda. Okay, that is the first formula. Next, you can see the order here. The long radio means the electromagnetic waves with lowest energy are your radio waves. So if they have lowest energy, they will have the highest wavelength, and the electromagnetic waves with highest energy are your gamma rays, and they are of high energy and low wavelength. Okay. Next, what happens? So this is about your black body radiation. So generally what happens whenever we have a black body, it emits radiations of all frequencies or it absorbs all frequency. That type of body is called as your black body. Okay. So now what was happening is, an ideal body which emits and absorbs radiation of all frequencies is called as a black body. Intensities of radiations of different wavelengths emitted by hot body depends upon the temperature. Now what was expected here is the energy emitted by the black body should increase dramatically. Means what happens when you the energy of the black body radiation should always increase, but actually experimentally it was found that, okay, in fact it suggested that at very short wavelength the black body would emit an infinite amount of energy. This was what expected, but what we found was the black body radiation, first the energy went to a maximum value and then it dropped. Okay, that was the reality that happened, and this particular experiment told us about the particle nature of the wave. Okay, next so we have the, now Planck came, and how was that reality and expectation, why it was different. So Planck gave us a true thing that nothing can have any energy value. So generally Max Planck suggested that energy could only be emitted or absorbed in discrete packets called as quanta or photons. Okay, so the quantized approach explained why energy did not blow up at a certain wavelength. So at a shorter wavelength also, why there was not that the energy can be anything, the wavelength can be anything, because only certain amounts of energy could be emitted at a higher frequency, not whatever you wish. Okay, next we have here photoelectric effect. So photoelectric effect is what, when a photons, when a light is falling on a plate, okay, electrons are ejected out from there. Okay, that is your photoelectric effect. What's the formula for this photoelectric effect? H nu. H nu is the energy of incident radiation. Okay, this energy which falls on the plate, that is your incident radiation. This is your threshold energy. Okay, threshold energy means again what, the energy, the minimum amount of energy that is required to remove the electron, and this is the kinetic energy of ejected electrons. Clear? Okay, next we will see the atomic spectra. So from here questions can be asked, so please remember. So whenever there is a transition of electrons from one energy level to the another energy level, energy is released. So the formula for that is 109677 into 1 by n1 square minus 1 by n2 square. N1 and n2 are the different energy levels. So based on that we have different types of series. So if your wavelength, or if your electromagnetic radiation from any other level is stopping at n1, then we call it Lyman series. Then from any other level, if it stops as second level, we call Balmer series, like Bastian, Brackett and P fund is there. This formula is important, please note down. Next we'll come to Bohr's model. So these are some Bohr's model. What are the important formulas you should be knowing? The first formula is the radius of an atom. So radius of the nth orbit, that is equal to a naught into a square into n square, where n is your orbit and a naught value is 52.9 picometer. Okay. Next we have energy of the orbit. So that is your minus RH 1 by n square, where RH value is your Rydberg constant. Okay, and then we have for any other species which looks like which looks like your hydrogen, means they have only one valence electron. Okay, these electrons, sorry, not one valence electron, they have only one electron in the system. Their radius also we can calculate, and it will be equal to 52.9 n square by z. Okay, the formula we know just now we wrote was what, Rn is equal to a naught into n square, right? Just you have to divide the z, the atomic number, and En value what we calculate, minus 13.6 z square by n square. Okay, if z is for any other atom or for hydrogen like atom, and this one will be in eV. If I want to calculate in joules, minus 2.18 into 10 to the power of minus 18 z square by n square joules. Okay. Next, what are the limitations here? So it fails to account for the finer details. So when you see the atomic spectra, in that lines also there were some small lines divided. It was not explained by your Bohr's model. Then splitting of lines in magnetic and electric field, that was also not explained. Ability of the atoms to form molecules by chemical bond, that was also not explained by Bohr's model. So next we'll see some questions here. With regard to photoelectric effect, identify the correct statement among the following. Okay, number of electrons ejected increases with the increase in the frequency of the incident light. No. So here you should remember, see, number of electrons will increase if intensity is increased, and the energy of the electron will increase if the frequency is increased. Okay, number of electrons ejected increases with the increase in work function. No. Number of electrons ejected increases with the increase in intensity. Yes, option number C is the correct statement. Next, the energy of an electron in the nth orbit of hydrogen atom. So we have 13.6, so z square, hydrogen atom is z is equal to 1 and by n square, right? So I need, yes, option number A, minus 13.6 divided by n square. Next, what is the ratio of the atomic radius of the 5th orbit in chlorine atom and 3rd orbit in helium atom? Okay, so I have this formula R chlorine. So I will first find for chlorine. So R formula is what? A naught by n square, A naught into n square. So I can write here A naught into, what is n value? 5 square, that is 25, and R of, I have helium atom, that is A naught into 3 square. Okay, so 25 by 9, 1 second, okay, n square by z is also there, right? So chlorine atomic number is 17, right? Chlorine atomic number is 17 and helium, hydrogen, helium 2. So I have here 25 by 17 into 9 by 2. So I will get 100 divided by 9 sevens are 63, 9 ones are 6 plus 5, 100 by 153, that is option number D here. Okay. Next, hydrogen atoms are excited from ground state to the state of principal quantum number 4. Then what will be the number of spectral lines involved? So the number of spectral lines formula is, number of lines formula is equal to n into n minus 1 divided by 2. Okay, so here n is your what? 4, that is your highest level. 4 minus 1, that is 3 divided by 2. So I will get here 6, that is option number B. Okay. Next, what will be the longest wavelength in the Balmer series of hydrogen spectrum? So you want to calculate, so I want to give you this as a homework, so please try this question and put in the comment section. I'll tell you how to solve it. So now you see that Lyman-Balmer, you have Balmer series means the series should end with at n equal to 2, okay, and you want longest wavelength. Longest wavelength means energy should be minimum, so energy will be very less if I am going from n is equal to 3 to n is equal to 2. So what will be my answer? So 109677, okay, so 1 by lambda is equal to 109677, yes. Then 1 by n1 square, so 1 by 3 square minus 1 by 2 square. Okay, sorry, I just made a wrong here. Yes, 1 by 2 square minus 1 by 3 square. So you can just solve this and put down the answer in the comment section. Let me see how many of you are doing this. Now we will move to next thing, that is your quantum mechanical model. So as we see towards to develop Bohr's model, what were the developments that took place before the Bohr model came? We had dual nature of electromagnetic radiation. People came to know about the particle nature of electromagnetic waves, and the next one was your hydrogen spectra. These two developments helped Bohr to give his model of atom. Now in case of quantum mechanical model also, there were some developments that took place. The first one is your dual nature of matter. There it was dual nature of radiation, here it is dual nature of matter, and Heisenberg uncertainty principle. After that we have here our quantum model. In quantum model, what were the postulates, what do you mean by nodes, what is quantum number, how to calculate the energy of the orbital, rules to fill the electrons, and electronic configuration we will see. Okay, so let us start with the first one. Here the first thing is your matter wave or dual nature of particle. So we already know that particle have particle nature, right? But de Broglie said that the particles can also have wave nature, and if they are having wave nature, they will have a wavelength, and how to calculate the wavelength of a particle. That formula was given, lambda is equal to h by p, where p is the momentum, or you can write h by mv, where m is your mass, okay, and v is velocity. Okay, clear? Next, if I see Heisenberg uncertainty principles, so it says that at the same time you cannot measure both the position and the momentum of an electron. If you measure position, there will be error in the calculation of momentum. If you measure momentum, there will be error in the calculation of position. So that is delta x into delta px will be greater than or equal to h by 4 pi. Okay. Next, so when we see that we cannot have a proper trajectory for the electrons, Bohr's rule or Bohr's postulates or Bohr's model of atom can be discarded here. Why? Because Bohr said that electrons travel in a fixed path called as orbits, right? So that is why it rules out the existence of definite paths or trajectories of electrons and other similar particles, and that is why we have, it means that the precise statements of the positions and the momentum of an electron have to be replaced by the statements of probability that the electron has at a given position and momentum. Okay, this is what the quantum mechanical model of the atom says. So what I can do is, now I cannot say that electron is present at this point of time. I can say that the probability of the electron to be present here is maximum. Okay, so that is what the term that electron is present has been now changed to electron might be present or may be present. Okay, so that is the difference, and this is what the quantum mechanical model tells us. Okay, now let us understand, so reasons why the Bohr's model failed. So I already told you the first one. In Bohr's model, an electron is regarded as a charged particle moving in a well-defined circular orbits about the nucleus. The wave character of the electron is not considered, right? So just now we de Broglie say that particles also have wave nature. They can also have wave-like nature. So in Bohr's model, electrons' wave nature was not at all considered. That's the first reason. And second, as we already discussed, an orbit is a clearly defined path, and this path can completely be defined only if both the position and the velocity of the electron are known exactly at the same time. This is not possible according to the Heisenberg uncertainty principle. Clear? Fine. Next, coming to the quantum mechanical model, what does it say? Postulates of quantum mechanical model. So here the possible energy levels and the electron can occupy corresponds to the wave function. So those areas where the electrons can be found were denoted by wave function. Okay, and the position of an electron can be given by quantum numbers, that is principal quantum number, azimuthal quantum number and magnetic quantum number. Okay, so these three numbers can determine the position of an electron. Okay, next, now the atoms are not present in orbits, they are present in orbitals, and orbitals are a well-defined space but not a path. Okay, we can say that in this space electrons can be present, okay, in this given space. That space is called as your orbital. Next, we have Bohr's model for one electron system. Similarly, we have quantum mechanical model for one electron system. Okay, so next, quantum numbers, if I see, before that we will discuss about nodes. So nodes are the reason where the probability of finding an electron is absolutely zero. Okay, we cannot find the electron at that position. So there are two types of nodes again, radial nodes and angular nodes. So radial nodes formula is n minus l minus 1, angular nodes is l. Okay, angular nodes is l, radial nodes is n minus l minus 1. Okay. Next, how to fill the energy. So the energy of the orbitals varies in this way. So first you have to fill 1s, then 2s, then 2p, then 3s, 3p, 4s, 4p, like this. Okay, just a minute, 1 second. Okay, here I missed the discussion of quantum numbers. So as I tell you, quantum numbers are of three types. Okay, like 4 types, but we'll first discuss principal quantum numbers. Okay, now principal quantum numbers are denoted by n, and its value can start from 1, 2, 3 and can go up to any value. It tells you about the energy of the shell. Okay. After principal quantum number, we have azimuthal quantum number, okay, denoted by letter L. Now, denoted by L, and azimuthal quantum number varies from 0 to n minus 1. Okay, what is the n value? To till n minus 1 I will have the azimuthal quantum number. It tells you about the angular momentum, okay, and shape of orbitals. Okay, next I have magnetic quantum number. Magnetic quantum number, it is denoted by ml. Its value changes from minus L to plus L, okay, and it tells you about the orientation. Clear? Now we'll take an example and understand this. So for example, just a minute, okay, yes. So for example, I have n equal to 1. For that L will be what? 1 minus 1, 0. ml values will be 0, okay, and this, if L value is 0, it is denoted as 1s, and I will denote it as 1s. If n is equal to 2, then L value will be what? 0 and 1, because till n minus 1, 2 minus 1 is this one. Here what I will have ml value 0, here I will have minus 1, 0 and plus 1, because ml values from minus L to plus L, minus 1 to plus L, okay. So here I have, this is 1s and sorry 2s now, because n is there, 2s. If L value is 1, we tell it as p, this is s, so it will be 2p, okay. So this is how quantum numbers work, and after that we have another quantum number, that is spin quantum number, and its value is plus minus half, denoted by ms, okay. Next we discussed already nodes, okay. Now how to fill the electrons? We have 3 rules here. Aufbau principle says that first the energies of the lower energies will be filled first after the higher energy, okay. First I will fill the lower energy orbitals, then the higher energy orbitals will be filled. Pauli's exclusion principle says that for 2 electrons the quantum numbers cannot be same, all the 4 quantum numbers cannot be same, okay. Next, the last rule, Hounslow rule, maximum multiplicity, says that if I have orbitals of the same energy, then electrons first should be given to all the orbitals, after that we should have pairing, okay. Suppose I have 3 orbitals, you want to fill 4 electrons, so you cannot fill like this, that is wrong. First you should give 1 electron to each, then you should start pairing, okay. These are the rules how we should be filling the electrons. So I'll just give an example. For example, I want to write sodium electronic configuration whose atomic number is 11. So I have 1s2, I have 2s2, okay, then I have 2p6, 6, 7, 8, 9, 10, then I have 3s1. So always remember, s can hold 2 electrons, p can hold 6 electrons, d can hold 10 electrons, and f can hold 14 electrons, okay. This is L values are 0, 1, 2 and 3, okay. Fine. Now we will do some questions. If the wavelength of a photon is this one, h is this one, then the momentum of the photon is. So we have this one, delta p into delta x is greater than or equal to h by 4 pi, right? What we have to calculate? Oh sorry, not this one, sorry. It is asking you, okay, we have lambda is equal to h by mv, right? So I want to calculate wavelength where momentum, so this is your momentum, right? So I am to calculate this one, so h by lambda. So what is the value of h? We know 6.6 into 10 to the power of minus 34, and then lambda value is 2.2 into 10 to the power of minus 11. So this will become 3 into minus 4 minus 1 3, and then I have 2 minus 23. So 3 into 10 to the power of minus 23, that is option number C. Next, the number of angular and radial nodes in 3p orbital, okay. So first I have to find angular and then radial. So angular is nothing but equal to your L value, so here L value is 1, so angular nodes is 1. Radial nodes is n minus L minus 1, so that is again 1, so option number B here, okay. Next, 2 particles A and B are in motion. If the wavelength associated with A is this much, the wavelength associated with B, whose momentum is 1/3 of A, okay. So for example, see, lambda 1 is equal to h by p1, I'll write lambda 2 is equal to h by p2. Now the question is saying that the wavelength of the wavelength associated with B, whose momentum is 1/3 of A, that means the momentum of B is 1/3 of A, right? So I can write, substitute this one. Let me just take the ratio of lambda 1 by lambda 2. That will be equal to h by p1. So I can get p2 by p1. Okay. Now if I just substitute here, I'll take it as a and b. So that will be more easy or convenient here. So I have lambda a by lambda b is equal to pa by pb. Okay. Now pb is equal to 1 by 3 of pa. So that will become 3. Okay. Here I can substitute. Lambda a is already given to me 33.33 nanometer. So if I divide this, I'll get 1.1 into, so that is your lambda b. 1.11 I will get nanometer. So it can be written as 1.11 into 10 to the power of minus 9 meter. So that will be, okay, just a minute. Okay, here it is 11, right? I'll get 11. So 11.11. So if I just take this one, I'll convert it. Okay, just a minute. 33, so 11.11, 33.33 nanometer. Okay, so I will get 11.11 into 10 to the power of minus 9 meter I got. Okay, now I can write it as 1.1 into 10 to the power of minus 8. Okay, so this is your answer, option number A here. Okay. Next, the orbital nearest to the nucleus, s orbitals are always nearer, so 4s. Okay, next, the correct set of quantum numbers for the unpaired electrons of chlorine atom. Chlorine atom, unpaired electron. So if I just write down the electronic configuration of chlorine, it is 1s2, 2s2, 2p6, 3s2 and 3p3, right? So n value will be definitely 3, right? N value is 3, so I can eliminate this option. P value will be 1, so that is option number D here. Okay. Next, consider the following sets of quantum number. Which of the following is not a permissible arrangement? So let us see here. So you can see if n value is 3, L value is 2, then ML value cannot be minus 3. So this is your option number D. Okay, so that's all, students, and I hope I have given you all the important concepts and topics that you should revise from this chapter. So please focus on Bohr's theory and then uncertainty principle, then your de Broglie's principle and quantum numbers. If you are done with these topics, this chapter is done for you. Thank you for watching, and please do not forget to subscribe the channel. See you soon in the next class.